Good morning, student. Today we'll discuss more about the determination of the height of back tower. Last day we have seen how to calculate the height of a back tower and we came up with this equation where this part is for height of a single transfer unit based on overall gas phase constant driving force. Okay, so capital KY, and this was a number of transfer unit based on overall gas phase driving force. And similar way, other forms are possible if I can use small ky, small kx, capital K's, and accordingly different expression will come that we have seen in our last lecture. Determination of H to OG is easy because G dash will be known, KY, that mass transfer coefficient, whether it is overall or individual, whatever you can calculate, that A, that is the mass transfer superficial area for mass transfer, that is meter square per meter cube of the packing. Generally, manufacturer will be given to you, and this also you can calculate based on your terminal concentrations. So the calculation of this part is easy and straightforward, height of the transfer unit, but number of transfer unit, that calculation it is little bit tricky because you have seen that we have calculated one there. There is a you have to do it numerically. Today what we will see that for little bit simplified cases it can be done. Okay, so if I don't make any assumption, then I have to do it this part numerically. That is correct. Okay, but let's take if the in case of dilute gases, means let's take you have a 2% ammonia in gas mixture. Okay, generally those are effluent gas. There are 1%, 0.5%, 2% ammonia is there, and you have to remove this one to 0.001%. So this is the case where dilute gases. So and in industry there are number of cases will be in this category, particularly that in those are environmental factors are there. So for dilute solution, the calculation of this number of transfer unit can be done analytically. Hence process will be easy. That's mean once I will learn this thing, how to calculate this thing analytically, and when generally problem will be given, you have to see if this your problem falls under dilute gases case, then you can use this equation. Okay, whatever we will derive, but otherwise this is the generic one. Everywhere it is applicable. So let's see how this term can be will be simplified for the dilute cases, and analytical solution will come. Now for dilute gases, 1 minus y, that will be almost equal to 1. Means let's take 1%. 1% means 0.01. 1 minus 0.01 means 9.99. So this is very close to 1. Okay, and ybm, that also will be equal to 1. So this is for the dilute cases, that assumption is true. So now if this assumption is true, okay, for dilute cases, then this will be 0 1 and this will be 1, so that nt og is comes as a dy y minus y star. And what is y star? It is the equilibrium concentration of x, isn't it? So if this is come now, it that analytical solution of this equation is possible. How? Let's take how it is coming. The equilibrium, if the equilibrium relation is linear, it is possible to evaluate the above equation analytically, assuming that the gas and liquid rates remain reasonably constant over the height of the vacuum. So this is true because when gas will flow, okay, there will be some change because of some, let's take ammonia, 1% ammonia is in gas and it is going to the liquid water. So some flow rate will be changed, but if you consider 1% only, it will change. So that's when you can consider that gas flow rate is constant. So if let's take you have put that 100 mole gas bottom, then 99 mole gas, if total absorption happen, 99 mole gas will go to the upper top. So only one mole will transfer from gas phase to liquid. So 100 to 90, you can 99 you can consider this is the constant. Similarly, liquid, if you take the liquid like 50 mole, now it would come 51 mole. So that's mean, so top you are putting 50 mole and bottom it is coming 51 mole if 1 mole transfer is there. So here that's mean you are that what dilute cases that assumption is correct. Okay, that you have to understand, which is true for dilute gas. That above equation, then it will, if you take that any if these things are not changed, so if you take extreme point 2 and any point y, so y whatever y minus y2, that whatever transfer will, that will come to x minus x2. So this will be the mass balance equation. So I can write x equal to g dash l dash y minus y plus x2. I can write. Now what is y star? Y star is mx, that equilibrium relation from this thing, because y star it is the equilibrium concentration of x. Now if I write that this term, what is this term? Y minus y star. This I can write y minus mx. Now what is x? X equal to this. So I can write y minus m l g dash l dash y minus y2 plus mx to this. So then I can write this one. Now what is this? L by mg equal to absorption vector. Okay, L by mg. Now it is 1 by, that's mean S. Okay, stripping factor. So this term is stripping factor S. So I can write y, I take the common, then this y and this, I take this y common from these two. So y 1 minus S for this one, then plus y2 S, S2 y plus minus mx2. Okay, so this will come. Now if you integrate this, dy this, then this term will come this. And for this equation, the analytical solution is easy. And what will be this solution? Now NTOG will be 1 by S ln 1 y1 into 1 minus S bar plus S bar y2 minus mx2 divided by y2 1 minus S bar plus S bar y2 minus mx2. So this will be my analytical solution. So here what you have to know, the absorption factor. Generally it will be known to you because you know the L by mg, y2, x2, y1, x1 will be known, and your equilibrium value, that is m, okay, Henry constant, will be known to you. So you can calculate that number of transfer unit analytically, but keep it in mind this is applicable only for dilute solution, because from the what is the governing equation is this. It is applicable for all, but this is applicable only for the dilute solution. Now this equation can be further simplified. Okay, how? Let's see how it can be done. Now I know that g dash equal to g dash from the material balance, g dash y1 minus y2 equal to l dash x1 minus x2. Now x1 by x2 equal to what? mx1. I can write, I can put it bottom m, and I can write up m. Okay, so I can put it this I can write this one. Now this is equal to L. Then what is this? This is equal to y1 star, and this is equal to y2 star. Okay. So now if I take this one, okay, this equal to this. So now this equal to this. So m g by l dash equal to this by this. So y1 star minus y2 star by 1 1. So this is will be my, this is equal to my s. Okay. Now what is 1 minus s? 1 minus s equal to 1 minus this. Okay. So this is equal to 1 minus y minus this. This is y1 minus y1 star minus y2 minus y2 star. So 1 minus s equal to this and s equal to this. Okay. Why I am writing this? Because here 1 minus s, 1 by s is there. So that's why I'll put this equation. So you don't, only that with equilibrium. Now let's see what will happen with this term. So this term is this. Okay. Now, now if you take this one y1 minus s into y1 minus y2, we take this here, okay, minus mx2. Now s equal to this. Okay, so I will put this s, this in this equation. I will put, and this term will be denominator y2 y2s plus y2s, it will cancel out. So y2 minus mx2. Now I will put s here, this s equal to this. Once I put this on, so this will cancel out. If it is cancel out, now y1 minus y1 star plus y2 star minus mx2, okay, by y2 minus mx2. Now mx2 equal to y2 star. So this, that it will be cancel out. So that term is coming y1 minus y1 star by y2 minus y2 star. Okay. So that means your now integer that equation comes, this equation becomes this. I will put this term, and for this term I will put this one. So then integer OG, it is coming y1 minus y2 by y1 minus y1 star minus y2 minus y1 star into ln 1 minus y minus y1 star by y2 minus y2 star. So now if you see, this is, now if you see, you can rearrange this equation. This is y1 minus y2 by this by ln this. I can put this, that's mean y1 minus y2 y minus y star m. Okay, y term is log mean driving force of the bottom and top, isn't it? So number of transfer unit is coming a very simple equation. You can put this one also, because here the terminal conditions will be known to you. So you know the y1 y2, you know the x1 x2, then your equilibrium constant is known. That's mean you know the y1 star y1. So you put this one, then directly you will get the your number of transfer unit. Okay, so for dilute solution, number of transfer unit can be calculated through analytical. Okay, and you know how to calculate the height of a transformer. That will be this way. Similarly, for approximate design equation for concentrated gases, when that gas will be very concentrated, so how it will be? See, this is my governing equation NTOAG. Now what will be YBM? YBM, then they are telling this is half. 1 minus y star plus 1 minus y two, because it is linear. Okay, so then if you put this term, then this equation become like this. Then if you have to integrate it, but in this case there is no, because ultimately have to go through the graphical or numerical. It is difficult. Better don't, for dilute concentrated cases you use this equation, that will be better, but dilute case you use this equation. Okay. And also for dilute cases, this is the case for dilute solution, isn't it? If you see, this is the case for the dilute solution. uh, Not this one. Sorry. This one. So this is the case for the dilute solution. For dilute solution, after that, if you don't take any this assumption, this type of assumption, if you calculate it directly, okay, if you calculate it directly, okay, with this equation, if you take the y equal to mx and then you solve it, okay, numerically, then that ntg will come this equation, ln 1 y1 minus mx1 by y2 minus mx2 into 1 minus s bar plus s bar by 1 minus s, this. But keep it in mind, this equation is called Coulomb equation, and this is applicable for the absorption in packed tower. Okay. But you should understand, in chapter 4 similar type of equation we have derived, that is the Kremscher equation. Kremscher equation is applicable for the plate column. Okay. And this, although it is looking similar, for dilute solution number of turns per unit you can calculate through this equation, and this is called the Coulomb equation. But don't mix this. Kremscher equation is, you can calculate the number of turns per unit, and that is applicable for the packed tower. And this Coulomb equation, it is very similar to that, but this equation is applicable for calculating number of turns per unit through Coulomb equation, but it is applicable only for the dilute case. Okay. So now I want to see that thing, design equation with concentration expressed in mole ratio. So still now what we have calculated, that is based on the mole fraction. Now we will see, if I take the mole ratio, that how the equation will be simplified, how does it look like, isn't it? So if you see, we have taken this equation, and here we have taken this one, gas flow rate per unit area. Gas flow rate per unit area. Okay. And we started with mole fraction. Now same calculation we will do, but we will take the mole ratio. When we will take the mole ratio, that means G dash S, this will be that, here G dash is varying, but now if you take the mole ratio, then G dash S will not vary, it will be constant, isn't it? So let's see how it is. So in this case, that is G dash Y. Then now in this case, what will happen? The change will be G dash S into dy. Here it was, change was, if you see, what change was d G dash Y. That means, that's why G dash Y, so I made it because both are changing. But in this case, G dash will not count. So change is dy. That will how much? So how much change will come? So that will transfer to the liquid phase. That is the A dH because unit area into Na. What is Na? Na equal to I can write small ky y minus yi small k capital Y. It is we are driving the expression in terms of mole ratio. And if you take the this is the individual mass transfer coefficient based on gas phase. Okay, small ky. But if I take this capital Ky, then it will be y minus y star capital Y star. Okay, so this is the thing. So this will be this. Okay. Now here we transfer this dt equal to this by this. So now if you take integration y to o g dash dy small ky ay y minus yi for this when we take the gas phase and overall transfer that will be g dash dy ky a into this. So now that means if you take this integration, now this equation you can take out of integration because here when g dash s will increase ky will increase. Okay, that will increase, that's correct, but then this is also increasing, this is a, but if you take the term whole as a, it will be constant generally, it is in sin the same what way we have taken the last one, but that time we use that ybf star, that here you need not. So this term is this. Now you can integrate dy y minus y1, this is for gas phase, and for overall thing g dash equal to y1 minus y2 to y1 dy this y minus y star. So this will be design equation. So now you have to integrate this one or integrate, isn't it? So if you integrate this one, then it the similar procedure you can. And if you see here we have, if you see here also we have seen this thing that when we have shown that what will be that in case of mole ratio. You see in mole ratio g dash capital K Y A, and this will be your equation. So same thing is coming, and so we make the calculation for this one and this one. Okay. Similarly, you can calculate all other part also. So it will come in similar way. Okay. It will be equivalent. So this thing will happen. So this is all about our the calculation of factor for absorption. So for a particular given problem, when you have to calculate the, you have to design the pack tower, your aim is, first name is what will be its diameter and what will be its height. You can calculate the diameter of the column, what we have discussed based in chapter 4. And in this chapter, we have seen how to calculate the height of the column. So height of the column, it can be divided in two parts: height of single transfer unit and number of transfer. Single transfer unit, it will calculation will be easy, and for calculation number of transfer unit, generally in general it will be, you have to do it numerically, but for dilute solution case it will be easy. So once you have got this one, then remaining part is very easy, because packing material what you will use, so accordingly you have to put this one. So according, now it is after, this is called process design. So after process design you have to do the mechanical part. So what will be thickness, how nozzles will be, in this thing. So all this mechanical design part you will learn in your process equipment and design too. That course, one lab course will be there. There you will learn in detail how to design, to make the mechanical, how to make fix the thickness of the cell, what will be nozzle, what type of nozzle, what type of support is required for this column. All these things will. But here, we have learned the main thing, that is that this is called the process design. So what will be diameter and what will be height of the column. And always our objective will be as a chemical engineer, how will I get the better separation with a smaller equipment. And for that one, whatever changes are required, you have to make. And how to make the changes are required, that also you should know. And this course will provide you the knowledge how you can make better separation in a smaller equipment. Thank you all. Have a nice time.